what is that magic formula doing? For example, it's supposed to produce a projection. If I multiply by a b, so I take p times b, I'm supposed to project that vector b to the nearest point in the column space. Okay, one way to recap is to take the two extreme cases. Suppose the vector b is in the column space. Then what do I get when I apply the projection p? So I'm projecting into the column space, but I'm starting with a vector, in this case, that's already in the column space. So of course, when I project it, I get b again, right? And I want to show you how that comes out of this formula. Let me do the other extreme. Suppose that vector is perpendicular to the column space. So imagine this column space as a plane, and imagine b is sticking straight up perpendicular to it. What's the nearest point in the column space to b in that case? So what's the projection onto the plane, the nearest point in the plane, if the vector b that I'm looking at is got no component in the column space, it's sticking completely 90 degrees with it, then pb should be 0. Right. So those are the two extreme cases. The average vector has a component p in the column space and a component perpendicular to it. And what the projection does is it kills this part and it preserves this part. Okay, can we just see why that's true? Just that formula ought to work. Let me start with this one. What vectors are perpendicular to the column space? How do I see that I really get 0? I have to think, what does it mean for a vector b to be perpendicular to the column space? So if it's perpendicular to all the columns, then it's in some other space. We've got our 4 spaces. So the reason I do this is it's perfectly using what we know about our 4 spaces. What vectors are perpendicular to the column space? Those are the guys in the null space of A transpose, right? That's the first section of this chapter. That's the key geometry of these spaces. If I'm perpendicular to the column space, I'm in the null space of A transpose. Okay, so if I'm in the null space of A transpose, and I multiply this big formula times b, so now I'm getting pb. This is now the projection, pb. Do you see that I get 0? Of course I get 0. Right at the end there. A transpose b will give me 0 right away. So that's why that 0 is here. Because if I'm perpendicular to the column space, then I'm in the null space of A transpose, and A transpose b is zilch. Okay, what about the other possibility? How do I see that this formula gives me the right answer if b is in the column space? So what's a typical vector in the column space? It's a combination of the columns. How do I write a combination of the columns? So tell me, how would I write your everyday vector that's in the column space? It would have the form A times some x, right? That's what's in the column space, A times something. That makes it a combination of the columns. So these b's were in the null space of A transpose. These guys in the column space, those b's are AX's, right? If b is in the column space, then it has the form AX. I'm going to stick that on the quiz or the final for sure, that you have to realize, because we've said it like 1,000 times, that the things in the column space are vectors A times x. Okay, and do you see what happens now if we use our formula? There's an A transpose A, gets canceled by its inverse. We're left with an A times x. So the result was AX, which was B. Do you see that it works? This is that whole business. Cancel, cancel, leaving AX, and AX was B. So that turned out to be B in this case.